Hello everyone, welcome to our next lesson in conic sections. This topic begins on page 33, and this is called the general second degree equation. General is different from the types we've been looking at so far. In fact, if you were to take all of those types of equations we've looked at, square out the binomials where appropriate, multiply both sides by any common denominator that there could be in those equations, and then group everything on one side, you'd end up with an equation that kind of looks something like this right here. A, B, C, D, E, and F are just constants. They're any real numbers, really. That's what we call the general equation. Now, remember how we were telling what these things were? Parabolas, remember, have one of the terms squared, one of the variables squared, but the other variable not squared. So in a parabola, for example, you would not have ax squared and something times y squared. That would not be in the equation of a parabola, not in the general form, not in any form, actually. What about circles? Well, what would happen here if you had a circle, the equation of a circle? Well, I'll guarantee you it would start with something x squared, and then there would be plus something y squared. Now, they may not have coefficients in front. They may look just like this, and if that's the case, the coefficient is actually 1, but you can tell it's a circle because they're both squared. They're added together. If there was a number in front, it would have to be the same number. That, for example, right there defines what a circle is. The next one would be an ellipse. Well, an ellipse in general form, you can tell because, well, you still have an x squared plus, and you still have a y squared. But if there are any numbers in front, they would be different now. So you could have something like 3x squared plus 5y squared, and then plus or minus something else. It doesn't matter what comes after that. Those two terms right there are enough to determine, to tell you that it's actually an ellipse. And for a hyperbola, in general form, well, remember now, you still have the x squared, you still have the y squared. The numbers in front could be different or they could be the same. The main thing is you've got a subtraction. So if you had something like 2x squared minus 3y squared, and then anything else after that, doesn't matter. That's a hyperbola. Or even, like I say, if you had 5x squared minus 5y squared. For a hyperbola, the numbers in front, the coefficients for the squared terms, could be the same. But anything after that doesn't matter. That will tell you what it is. It's definitely a hyperbola in that case. By the way, the only time, let me just go back and look at the general equation again. Do you notice that one of the terms there is b multiplied by xy? The only time you get that term show up is when you have the simple equation, the simple form of the hyperbola. And we saw that. That would just be something like x times y, well, equals 10. Or something like that. Of course, in general form, you'd probably have the 10 over subtracted from the xy. So what is this topic all about? Okay, well, how is the general form different from the other forms we've been looking at? Well, the fact is they are different. And what we're going to see in this chapter right here, in this section, is we're going to see how do we take an equation that's in general form, like that looks like some of these here at the top. How do we take those and change them back into the standard form that we've been looking at so that we can tell exactly where the center is, or vertices, or any of the other things that we were finding, we were looking at and determining from the equations in the other form. So that's what this is all about. And it starts by, first of all, reviewing something called completing the square. Now, back in Math 1700, you looked at a technique for solving certain types of quadratic equations. In fact, you can solve any type of quadratic equation using a procedure called completing the square. Now, in order to use that procedure, that technique, you had to recognize when a trinomial, these are all trinomials right here, when is a trinomial what we call a perfect square trinomial? Well, if you look at it carefully, let's look at the first one, for example, x squared plus 4x plus 4. what you do is you look at the middle term, the number in front of the linear term. In this case, it would be a 4. You take half of that, and then you square the result. So a half of 4 is 2. And when you square the 2, square that result, you end up with a 4. And do you notice that there's a 4 here on the end? Now that's going to be true for all of these perfect square trinomials, every single one of them. Notice it's always a plus on the end. It has to be a plus for a perfect square trinomial, because a perfect square trinomial can be written as the square of some binomial. And when you square a binomial, meaning when you multiply a binomial by itself, you always end up with a plus on the end. It has to be, no matter if it's x plus 2 or x minus 2 or whatever. Look at this middle term. That's an 8. Well, if I take half of 8, I get 4. And if I square 4, I end up with 16. And sure enough, that's the number that's on the end. And in fact, that's the procedure, that's the technique that you have to do when you're doing something called completing the square. That was the method that you learned for solving certain quadratics back in Math 1700. So all of these questions we're going to do here right now, every single one of them, involve that completing the square technique. And we're going to look at all of these examples now. These are on page 34 in your notes. And I'm looking through these examples here. And well, first of all, there's example number 1. Example number 2, there's several of them there. So what I'm going to do is just very quickly look at example number 1. And the first thing I'm going to ask you is, what is that? What is that? Which of the 4 conic sections is that? Is it a parabola, or is it a circle, or is it an ellipse, or is it a hyperbola? Well, it's all got to do with those 2 terms in front, the squared terms, if there are 2 squared terms in it. I can see I have an x squared. I can see I have a y squared. I can see they're added together. They're both positive. And, well, you can consider them both having a coefficient of 1. They're alike. So that tells me right away, they tell you here anyway, but that tells me it's a circle. If you look at example number 2, part A, there is another equation in general form. And what do you think this is? Oh my goodness, it starts just the same way as the last one. Did you see that? X squared, y squared, so it's not a parabola. There's a plus sign between them. They're both positive added together, so it's not a hyperbola. And the coefficients in front, well, they both look like 1 to me. Well, this one's a circle. All right. So really, example 1 and example 2a are the same types of problems, the same one. If you can do one, you should be able to do the other. So what I'm going to do is come down here and look at example number 2. I'll leave example number 1 for you to try. And we're going to take this circle, and it is a circle. We're going to change it into the other form, the standard form, so that we can actually see what the center and the radius is. You see, there's a problem with having equations in this general form. Oh, if you want to get the center of this circle and the radius of this circle, right now, I have absolutely no idea what they are. None. I can't see what the center is, and I certainly cannot tell what the radius is, not in general form. And that's one drawback to having an equation, a conic section in general form. So here's what we do. Here's the procedure that we go through. We're going to have to complete the square here twice, because remember, we want to end up with 2 terms that are squared, right? Like x minus h squared and y minus k squared. Those are binomials, right? We need to write these as the squares of binomials. So here's the procedure. Watch what I do. I'll put my x squared and x terms together. So there you go. You've got x squared plus 4x. All right, so I just put them together. That's all I did. Now, I'm going to put a set of brackets around them, and I'm going to leave a little bit of space on the end. Okay, plus for circles, this is the simplest case. This is all you really need to do. Now I'm going to have another set of brackets, and by golly, I'm going to put the y squared and the y terms together. Okay, see what I did right there? And I'm going to put another bracket enclosing that. I'm leaving a little bit of space again. And the other thing that I'm going to do, ladies and gentlemen, is the constant, the plus 24. I'm going to throw that over onto the right-hand side of my equation. And what's going to happen there is it's going to become a negative 24. Well, let's just do that. Okay, so far so good. We've got everything set up. Now, let's look at each individual set of brackets. Let's complete the square. And remember how we do that. You look at the term that's in the middle, like here it's a 4. There's no coefficients in front of the squared part. If there was, I'd have to remove that. I'd have to take that out in front of the brackets. That would have to be removed. So a half of 4 is 2. And then if I square 2, I end up with 4. So I'm supposed to add 4 here onto the end. That becomes added. The next one, I have y minus 12, y squared minus 12. Half of 12 is 6. 6 squared, it becomes 36. So I add that. I add the 36 right there. Okay? Now, by the way, when I added those terms, I kind of fooled up my equation. I can't just take an equation and add 4 to one side and not somehow fix that equation. Or I can't add 36 to one side of an equation and not somehow fix it. So what I need to do here now is very carefully look at what I did. What did I just do to the left side of my equation? Because whatever I did, I have to fix it up on the right-hand side. So you will notice that what I did right here inside those brackets, I added 4. And I really did add 4 to the left-hand side. So on the right-hand side, I come over and I must add 4 to that side as well. Remember the fundamental rule of algebra. Whatever you do to one side of an equation, you have to do to the other side as well. Okay? So I added 4 to the left. I added 4 to the right. Now, right here, I added 36. Well, that threw my equation off. My equation is no longer correct. It's no longer valid. But to make it correct, to fix things, if I add 36 to the left, I must add 36 to the right as well. Remember that. Whatever you do to one side, you have to do to both sides. Okay, now we're going to write these as the square of some binomial. And remember, the easiest way to do that, you know the first term is going to be x. You can either, the sign there in the center, by the way, tells you what the sign in the middle is. Now you can either take the square root of the number on the end, which in the first case would be 2, the square root of 4 is 2, or you could think of it as taking half the middle term. Either way, you're going to end up with the same number. So a half of 4 would be 2, or the square root of 4 is 2. So there you go. That's x plus 2 squared. That's what my first binomial will become. Now what about the second one? This is going to start with a y. The sign there in the center, that tells you what the sign is in the middle of my binomial. This is going to be a minus something. Now you can either think of what is the square root of 36. All right, and you all know that 6, I hope. Or you could think of it as what's half of 12. And that's 6 as well. So 6, like I say, it doesn't matter how you do it. You're going to get 6 in either case. So this becomes y minus 6. Don't forget your squared is equal to. Now look at what we have on the right side. You've got a bunch of numbers to add up. You have negative 24 plus 4 plus 36. And if my old brain serves me correctly, that should be 16. And now look at what you've done. Look at that equation. Now it looks like a circle. Now it looks like the forms that you've been using over the past few videos. And I can easily now look at this and I can tell that my center is what? Look after the x. What comes after the x? Change the sign. So that's negative 2. Look after the y. What comes behind the y? It's a minus 6, so that changes to a plus 6. And not only that, ladies and gentlemen, I can tell what my radius is. My radius is the square root of the number on the right side. That would be 16, and by golly, that's 4 units. So what we did was we took the equation of a circle in general form, and we changed, or in standard form, sorry, and we changed, oh no, we took it in general form and we changed it back into standard form where I could see what the center and what the radius is. Okay? Circles are the easiest ones to convert, I must say. The other ones are going to involve a little bit of other workings, but we're going to do some examples there now, though. We're going to try some down below. Let's look at B. B says find all indicated points of interest for the ellipse given by the equation. And now, well, first of all, they didn't have to tell us it was an ellipse. We should have been able to figure that out just by looking at the two terms there in front. X is squared, y is squared. They're added together, but the coefficients are different, and that's why I know that's it's an ellipse. Now, when they say all indicated points of interest, that would be things like the vertices, the co-vertices, the foci, the center, all those things like that, right? Well, I'm going to just change that form now from general back into standard. And we start by doing it pretty much the same way we did with the circles. Watch carefully. Let me get my marker ready. I'm going to group together the 9x squared minus 18x. All right, I put those together inside of a set of brackets. And then I go plus. And what do I put in the next set of brackets? Well, how about 4y squared plus 16y? And I close that off with a set of brackets. And just like I did for the circle, I'm going to take that plus 16 and I'm going to throw it over to the other side. It's going to become a minus 16. All right, so far so good. But we got a problem. We got a little problem. And here's the problem now. We cannot go ahead and actually complete the square just yet because of these coefficients. Look at that. You see that? That's not just x squared. That's 9x squared. You can't complete the square with a 9 in front of that x squared. And we don't just have y squared. We actually have 4y squared. So what we have to do here, ladies and gentlemen, before we even begin to complete the square, we have to remove the coefficients of those quadratic terms. Even if you basically divide everything in the brackets by 9 in the first case and everything in the brackets by 4 in the second case, even if they're not common factors. Like if that was 9x squared minus 17x, sorry, you'd still have to divide by 9. Now you'd end up with a fraction for your middle term, but that's the breaks. So here we go. Let's take the 9 out in front. So I'm going to have x squared. Now negative 18x divided by 9. Remember, you're removing it as a factor. So that will become minus 2x. Now leave a little space because you're going to complete the square there next. And then I go plus 4 comes out in front of the second set of brackets. You have to divide both of those terms by 4. You're going to have y squared plus 4y. Leave a little space. Equals minus 16. Okay, so far so good. Now, let's complete the square twice. Let me see. You look at the middle term again, remember? So here I've got a 2 in the middle. Over there I've got a 4 in the middle. Okay, so let's look at the 2. Half of 2 is 1. 1 squared is 1. So I go plus 1 right there in that set of brackets. And now I have forced that trinomial to become a perfect square trinomial. But remember, I just did something, well, not bad, but I just did something that I've got to fix now. I just wrote down plus 1, didn't I? How do I rebalance that equation? Should I add 1 to the right side? And the answer is no, I don't. Because you know what? I didn't really add 1. Look what's out in front of that set of brackets. There's a 9 out there in front. That 9 actually multiplies by the 1. So when I wrote down plus 1, and yes I did, I wrote down plus 1, what I really did in essence on the left side was I added 9, not 1. So if you want to rebalance your equation, you better come over to the right side and you write down plus 9. Now that rebalances my equation. Now everything is nice and fixed up once again. All right, but I didn't really add 1, I really added 9. And not only that, let's do the completing the square here now for the second set of brackets. Okay, I've got a 4 in the center. Half of 4 is 2. 2 squared is 4, so I add 4. Okay, now, did I really add 4, though? Did I really add 4? I wrote down plus 4, but out in front, there's another 4, you see? There's a positive 4 out in front of that. 4 times 4. I really added 16 there, didn't I? So if I want to rebalance my equation, on the right-hand side, it's 16 that I have to add, not 4. Okay, and now everything should be okay. Everything should be nice and balanced. All right, now, because you have forced these to be perfect square trinomials, we should be able to write them as the square of some binomial. So I've got 9 in front of something squared, and then I've got 4 in front of something squared is equal to, we'll figure those out now in just a second. And on the right side, look what you have. You have negative 16 plus 9 plus 16. How about 9? Okay, so what are the binomials that go in those brackets? Well, x squared minus 2x plus 1 is going to be x minus, and now you can think of the square root of 1, which you know is 1, or half of 2 is 1. Either way, you're going to get 1. And for the second set of brackets, you're going to have a y. The sign in the middle is plus, so this is going to be plus something, and the square root of 4 becomes 2, and there you go. All right, wait a minute. That still don't quite look like an ellipse, does it? Because remember now, usually there weren't numbers in front, although we could fix that. But that 9 on the end, that's what's kind of making things a little difficult here. So what we need to do, we need to turn that 9 on the right side into a 1. So watch what I do. I divide everything by 9. Everything. All the terms. And now what I need to do is, I need to reduce these fractions as much as possible and make sure none of those numbers, none of those coefficients are left in front. There should only be denominators in this case. Well, in the first case, the 9s just cancel, don't they? So you're left with just x minus 1 all squared. You can put that over a 1 if you like, but it's not really necessary. Now, look at the second fraction. Be careful with that. 4 is not divisible by 9, is it? But you want the 4 to disappear. You want that 4 to vanish. So what would you do to the numerator and the denominator to make that 4 disappear? Well, I'll tell you what you could do. What if I divided by 4 in the numerator and also divided by 4 in the denominator? And now the numerator is gone. Look at what you have left now in your denominator. It's 9 over 4. 9 over 4. And actually, that's bigger than 1. So for an ellipse, that's your a squared. And on the right-hand side, of course, you just get 1. So now, believe it or not, you have actually completed the square twice. You have actually taken that equation, you have changed it from general form, and let me write the final answer right here. I'm trying to make a little bit of room for myself. X minus 1 squared, and you can put that over 1 if you want, like I say. And then you have a plus, and then y plus 2 squared divided by 9 over 4. Now, it's not often you get a fraction in a denominator, but in this case we did, and that's equal to 1. And now, of course, you could go ahead, and the problem, remember, said find all indicated points of interest. Well, you can easily get things down like the center. You can tell which way this ellipse is elongated. Is it stretched vertically or is it stretched horizontally? And then you could go ahead, just like we've done in the previous sections, and you could also go ahead and find things like the vertices and the co-vertices and the foci. Remember now, if you put this first one over 1, 9 over 4 is bigger, isn't it, than 1? So that's your a squared, and the 1 is actually your b squared. So that's how you would start doing these calculations. And because the larger number is under the y, this ellipse is actually stretched out, something like that, stretched out vertically. Okay? So I'll tell you what, 25 minutes have gone by. I'm going to stop this video, and I'm going to come back and do part C and D, yes, but I don't want to like, belabor this. I don't want this video to go on too long. So I'll stop and start another video using parts C and D. All right, so I'll see you again in just a moment.